All right, today we're going to break down one of the most fundamental forces that powers our world, current electricity. We're going to get right into what it is, how it works, and yeah, how we actually measure it.
So you look at these two things, a huge, wild bolt of lightning and, a simple flashlight. They seem totally different, right? One is just this massive, chaotic burst of energy, and the other is a small, controlled beam of light. But here's the thing. At their very core, they're the exact same phenomenon. It's all about a flow of electric charge. So what exactly is this flow? Okay, let's dive in.
Okay, so to really get a handle on what current is, we're going to start with a really powerful analogy. It's a simple idea, but trust me, it's the perfect way to start thinking about this.
Just picture a river. You've got water constantly moving past you, right? Well, electric charge acts in a really similar way inside a wire. Think of the individual charges like they're little water molecules. The electric current, that's just the rate at which that water, the charge, is flowing past a certain spot. It's all about movement. How much? How fast?
All right, so we've got this great mental image now, right? Charge flowing like a river. But how do we actually put a number on that? I mean, how do we measure the strength of that river? Well, lucky for us, physics gives us a really precise and honestly pretty straightforward way to do it.
It really just boils down to a simple ratio. All we need to know are two things. First, the total amount of charge that passes a point. And second, how long it took for that charge to pass. That's it. Current is just the relationship between those two things, how much charge and in how much time.
And that brings us to the key formula right here. I equals Q divided by T. Now, I is just the symbol we use for current. T is our time, in seconds. And Q, that stands for charge, which we measure in something called coulombs. So what on earth is a coulomb? Well, get this. It's a massive amount of charge. We're talking about 6.24 quintillion electrons. That's a number with 18 zeros. So when we're talking about even one single coulomb flowing, we're talking about a mind-boggling number of charges all moving together.
Okay, let's make this real with a quick example. Let's say we measured 12 coulombs of charge flowing through a wire. Again, that's a colossal number of electrons. And we pull out our stopwatch and see that it took exactly 3 seconds for them to pass. So we just plug those numbers into our formula. Current I equals 12 coulombs divided by 3 seconds. Simple math, right? The result is 4. And the unit we use for current is the ampere, or amp for short. So we've got a current of 4 amps.
So is 4 amps a lot? To put it in perspective, your phone probably charges at around 1 or 2 amps. But let's go back to that lightning strike we mentioned earlier. An average bolt of lightning can carry a current of, wait for it, tens of thousands of amperes. It's just a truly mind-boggling amount of charge moving in a split second.
I mean, that scale is just incredible. But it makes you wonder, right? How does that flow even get started? Well, to figure that out, we have to go from the scale of a thunderstorm all the way down to the atomic level. So let's zoom way in and see what's actually happening deep inside that wire.
Okay, so inside any piece of metal, you've got this kind of sea of free electrons. These are electrons that aren't really tied to any single atom, so they're free to just roam around. And they do. They're zipping around like crazy, bouncing off everything. It's total chaos, kind of like bees in a swarm. For every electron moving one way, there's another one moving the opposite way. The end result? There's no overall net direction. And if there's no net flow, there's no current. Simple as that.
So if it's all just random chaos inside the wire, how in the world do we get that useful, steady river of charge we need to power something like a flashlight? Well, we need to give those trillions and trillions of electrons an organized push, all in the same direction. And this is where the magic really happens.
What you're seeing here is the key. We apply something called an electric field. You see it represented by those lines in the letter E. The best way to think about this field is that it creates a gentle, consistent slope for our river of charge. It's the thing that gives it direction. So how do we create this field? Easy. That's exactly what a battery does. It creates a positive end and a negative end on the wire. And that separation of charge is what establishes the electric field, that letter E we saw. It always points from the positive side to the negative side, creating that slope for all those charges to start following.
Okay, but here's a super important detail. Electrons are negatively charged. So what does that mean? It means they feel a push from the electric field in the opposite direction. They get pushed away from the negative end and pulled towards the positive end. Now, they're still doing their random chaotic bouncing around, but on top of that, there's now this overall slow drift in one direction. And that tiny, consistent drift, when you add it up across trillions and trillions of electrons, that is the electric current that powers our world.
All right, that was a lot. We went from a river to a lightning bolt,
all the way down to the microscopic dance of electrons. So let's just quickly pull it all together and summarize the key takeaways. So here's the bottom line. Electric current, which we call I, is just the rate of charge flow. The formula is super simple. I equals Q over T, charge divided by time. The unit is the ampere, or amp, which is just 1 coulomb of charge flowing past a point every single second. And how does it happen? An electric field makes all those free charges inside a conductor drift in the same direction. That's the whole shebang.
And that leaves us with one last, kind of mind-bending question to think about. If the individual electrons themselves are drifting so slowly, I mean, we're talking snail's pace here, why does the light turn on the instant you flip the switch? Think about it. The answer is that the electric field itself travels at nearly the speed of light. It's like a chain reaction. The field tells all the electrons in the wire to start moving at practically the same time. It's like turning on a garden hose that's already full of water. The water at your end comes out instantly, even though the water from the faucet has to travel the whole length. It's a fantastic puzzle, right? And it really highlights the difference between the speed of the electrons themselves and the speed of the signal that pushes them. Really cool stuff to think about.